Welcome, ladies and gentlemen, to Integrated Math 2. In today's episode, we will be discussing Chapter 3.1.2, which is the tree model. The tree model is used to calculate probability, just like the area model we did in the previous section, but there's just a different visual aspect to it. And so we're just trying to give you different tools on how to calculate probability. There will be times when the tree model is going to be necessary over the area model, but when we get there, we will definitely explain how that works. And so we'll begin with problem 3-12. It says your teacher challenges you to a spinner game. You spin the two spinners at the right. The first letter comes from spinner 1, the second letter comes from spinner 2. If the letters can form a two-letter English word, you win. Otherwise, your teacher wins. Test your ideas with the spinner provided in the spinner game. So after a few times spinning the spinner using the E tool, we're supposed to determine if the outcomes are independent of each other, and absolutely they are, right? The outcomes are independent because spinner 1 has no impact on spinner 2. So now in part B, they're asking us to draw an area model of the sample space, and then we're going to calculate the probability that we're going to win this game. And so let's go and do it real quick. The area model will look like this. I'll go ahead and choose to put spinner 1 on the side and spinner 2 up top, which means the spinner 1 diagram will have 3 rows. Spinner 2 will have 2 columns. And this is the letter I, this is the letter U, and this is the letter A. This is the letter T, and this is the letter F. And so now from here, let's go and throw down some individual probabilities so we can find out the probability of getting each letter. So before I do that, let's go and take a look at the diagram here. Spinner 2 is actually quite straightforward, right? You have a 1/4 probability of getting a 4, a 3/4 probability of getting an F. So let's go and write that down real quick. 1/4 for the true, 3/4 for the false. Now from here, in spinner 1, it's easy. One half for the I. But it's easy to look at this U and say that he's 1/3, right? Because it looks like he's 1/3 of the circle. But remember, he'd be 1/3 of that if this part was true, okay? So because he's only half of that 1/3, that means that the probability of getting a U is 1/2 of 1/3, which is 1/6. And now from here, the probability of getting the rest of that is going to be the rest of the half that's remaining. So in this case, it'll be 2/6, right? Because 2/6 plus 1/6 is 3/6, which is the other half of the circle. I'll go and reduce that and make that 1/3. And I'll go ahead and erase him now because I don't want to get confused with too many numbers on there. So hopefully the way I got the A and the U makes enough sense. A little bit of a trick with that problem there. They'll definitely try to mislead you, so don't fall for that. Let's see here. We're looking at the probability of getting an I and then a T. So remember, the probability of those two guys together will be the intersection of their dimensions. So 1/4 times 1/2 is going to be 1/8. 3/4 times 1/2 is going to be 3/8. 1/4 times 1/6 is going to be 1/24. And then 3/4 times 1/6, so let's see, 3/4 times 1/6, that's going to be 3/24 or 1/8. And then 1/4 times 1/3 is 1/12, and then this guy will be 1/4 here. I'll go and erase him because I don't need him anymore. So let's go and calculate the probability that we're going to win. So the probability that we're going to win is going to be, change tools here. Okay, so I'm looking at only 3 words that can be formed here. The probability of it being formed, the probability of at being formed, and the probability of if being formed. I think those are the only words that can be made from this spinning diagram here. The probability of an it is going to be the intersection of the I and the T, so that's going to be 1/8. Probability of at is going to be 1/12. And the probability of an if is going to be 3/8, right? Probability of if. Yep, 3/8. Cool. So now we're going to add all those guys together. Remember, why is it adding? It's because the probability of this or the at or the if. So from here, let's go and combine some like terms here. I'm going to get 4/8 plus 1/2, which is going to be 1/2. Sorry, not 1/2, 1/12. There's going to be 1/2 plus 1/12. So let's go and get a common denominator here. So that's going to be 6/12 plus 1/12, which is going to be 7/12. So the probability ultimately of you winning, the probability of a win for you is going to be 7/12. So now the question C is going to ask you, is the game fair? If you played 100 times, who would win more often, you or your teacher? And so from here in question C, we can answer the question. Now check it out. The probability of you winning is over half, okay? And so even though we might think that's fair because it makes us feel good because we're winning more than half the time, that is actually the definition of unfair. So we can say the game is not fair because we are winning slightly more than half the time. If the game was going to be fair, both players need to have an equal probability of winning. And there you have it. There is 3-12. So a pretty basic question. We haven't done the tree model yet, and don't worry, I know that's the point of the lesson, but we will go into the next problem here, and I think they're going to ask us to make a tree model out of this, so I'll be back in a flash. In 3-13, we're talking about Sinclair, who drew the tree diagram to demonstrate the same probability as the area model. So if you see the letters are still there, notice the reason why it's called a tree diagram, right? It's called a tree diagram for a reason. And it's because all of the different outcomes are looking like branches. And so that's why they call it a tree diagram. So Sabrina, off the cuff, says that can't be right. The diagram makes it look like all words are equally likely. What is Sabrina talking about? Well, Sabrina is talking about how, without labeling the individual probabilities, all probabilities look the same. So this is why in the area model we have to label the individual probabilities in those boxes. Otherwise, all the dimensions look the same. So let's write that down here. Sabrina is talking about how each branch does not yet have a labeled probability. So everything looks equally likely. And now in part B, they're saying, let's mark all of the branches to show their individual probability. So give me a second. I'll be back. I'll just give you guys the diagram to not waste time. And we're back in part B with all the pieces labeled right there. I expanded the diagram and I marked each branch with its own respective probability. In part C, it says, according to the probability area model you made in 3-12, the last problem, what is the probability that you will spin the word at? Now examine the bolded branch. That way we can figure out its probability based on the tree. So the probability of an at based on the last problem here. Let's go and scroll up here. The probability of the word at was 1/12. According to our area model. Okay, so now from here, let's go ahead and find out using the tree diagram how we would get that. So from here, to spell the word at, we'd have to spin the letter A and we have to spin the letter T. So the 1/3 had a chance, was the probability of A. The 1/4 was the probability of T. So how do those guys combine together to become 1/2? Well, just like the area model, we multiply those probabilities together, right? Just like how the base meets the height, the branch meets the branch. We multiply them together. So let's go and write that down. We get this probability by multiplying the branches of A and T. And there you go for C. That's how you do it. And now it says, does this method work for all the other combinations of letters? Similarly, calculate the probabilities of each of the paths of the tree. So what they want us to do is the probability of it would be 1/8. The probability of if would be, looks like 1/2 times 3/4. So that's going to be 3/8. 1/6 times 1/4 is 1/24. 1/6 times 3/4, I'll go and just multiply that out. So that'll be 3 over 24, or 1/8. And then at was 1/12. We already got that. And then this will be 1/4. And do those match? Yes, they do. The it is 1/8. We saw that in the area model here, the 1/8. So what we're trying to get you to see is we're trying to get you to see the corresponding of the branches to the individual areas. So if was 3/8, right? If was 3/8, which was right over here. Now, does if have a 3/8 probability according to the area model? It does, right? It's right here. Right, so they're trying to get you to see the probabilities match up. So that would be part D. Awesome. Part E says identify all the branches with the combinations that make words, and then let's find out if the probabilities match up. So it, if, and at were the words. So that became 1/8 plus 3/8 plus 1/12, and I believe we did that problem already up here and got 7/12. So we are all good. So again, what is this chapter about? It's about trying to relate the tree model back to the area model. It's just a different way of looking at probability. I'll be back with the last problem. All right, in 3-14, we're talking about a rat trying to go through a maze here. And it says Ryan has a pet rat, Romeo. He boasts as the smartest rat in the country. Sammy overheard Ryan, and they're going to make a maze. So again, after a lot of exposition, we're just trying to figure out which room he's going to end up in. And so in A or in B, it says he placed the cheese in an airtight container. Okay, so basically, yeah, we're not going to use smell tracking in order to, figure out what room he ends up in. Okay, it says, suppose every time Romeo reaches a split in the maze, he is equally likely to choose any of the paths in front of him. That's important. And so choose a method to calculate the probability that he'll end up in each room. And then let's go and just use the tree model. And we can explain why the tree model, because one, it already looks like a tree. Second of all, that's the point of this chapter. So in part A, we'll go and draw a tree diagram. So here's the rat. He's gonna start from the beginning, and at his first juncture, which is right here, his first juncture is right there, right where I just drew that purple vertical line. He has 3 paths to take, if you guys can see that, 3 paths. So I'll go and draw that right now. His 3 paths is he could take this path, or this path here. Remember, each one has an equal likelihood of happening, so they're all going to be labeled as 1/3. Now, from this juncture here, I'll go and highlight this in green. From this juncture point right here, the top juncture, he can go 1, 2, or 3 paths again. So 1, 2, 3 paths again. Again, all equally likely to happen. Now, if he takes the first and second juncture, he ends up in space B. If he takes the bottom juncture, he ends up in space A. If he goes the middle for the first path, he automatically ends up in room A. So we can just label that in there. The bottom junction point right here, if I label it in yellow, and it's hard to see on the white background, but he has 2 options. He can either go up or down. He can go up or down. Each one has a 1/2 chance of happening. If he takes the top path, he'll end up in A. If he takes the bottom path, he'll end up in B. So what we're going to do is we're going to figure out the probability of him ending up in each room based on where he started. So from here, in order for him to end up in room B from the top, he'll have to take a 1/3 juncture and a 1/3 juncture, which means probability of room B at the top is going to be 1/9. Again, multiplying the branches together, we talked about that in the last problem. In room B from the middle, or from the second from the top, again, 1/3 times 1/3, again, that's going to be 1/9. Room A is going to be 1/9 again. This room A right here is going to be 1/3. How is this A 1/3? Well, remember, this is from the first split, right? He has a 1/3 chance of going up, 1/3 chance of going sideways, 1/3 chance of going down. So that's just going to be 1/3 based on the initial choice. Room A again, 1/3 times 1/2 is going to be 1/6. And then this is going to be 1/6 as well for room B. So now it says if he moves through the maze randomly out of 100 attempts, how many times would he expect to be in room A? So the probability of A happening, and then the probability of room B happening. So remember, he has multiple different options for each one. So these are all OR choices, right? The probability of room A, don't miss out on this guy, is going to be 1/9 plus 1/3 plus 1/6. And after getting all the common denominators and adding them up, that ends up being, let's see, 2 over 18, 3 over 18, and, 6 over 18 is what I meant. 6 over 18 and 3 over 18. That's going to be 8, 11, 11 over 18 chance of ending up in room A. In room B, that's going to be 1/9 plus 1/9 plus, so I took care of this guy and this guy, and then another room B plus 1/6. So 18 is the common denominator here, so I'm going to go 2 over 18 plus 2 over 18 plus 3 over 18. So that's going to be 4, 7. 7 over 18 chance that the rat will end up in room B. So in part B says, if the rat moves through the race randomly after 100 attempts, how many times will you end up in the room? So what they're asking us to do is they're asking us to convert this into percentages. So this is 11 divided by 18 is really 0.61, which is about 61%, so about 61 times. And the probability to end up in B is going to be 7 over 18. So again, you'll probably just use a calculator for this. 0.389, or about 39%, about 39 times. He'll end up in room B. Now it says, after 100 attempts, Romeo has found the cheese 66 times. And he says, see how smart Romeo is? And clearly he learned something and got better at the maze. Sammy wasn't so sure. And then we have to figure out, do you think Romeo learned and improved on his ability? Or could he have been moving it randomly? This is a pretty subjective question. I mean, honestly, they could have been putting the cheese in the same spot every time, and then the rat learned how to get the cheese from that room. You know, it's kind of a weird question to ask. I mean, it's, you know, that gets more into something else. Okay, I think that'll wrap it up for this lesson. Again, the tree model, area model, 2 different ways of calculating probability. I will see you all in the next video. Please make sure you leave questions or comments in the comments area, and I'll see you in the next episode.